Hello everyone. Let me introduce myself first. So my name is Hossam, not Hassan. Okay, it doesn't matter. So I'm an offensive security researcher in Halborn. I'm doing pretty much L1 audits, just general security research. Of course, smart contracts audits. I'm more focused into Web 2. So I've been working before that. Have been into cybersecurity space, doing security tooling, evasion, and vulnerability research for sure. And yeah, I'm a member of SWAT team in Halborn, which is like a small team of like just SWAT team. I don't need to explain that much too much. So today's agenda, we're gonna talk about like what's that research motivation. We're gonna talk about some basics about a certain virtual machine. We can like explain like the EVM bytecodes, breaking down the EVM bytecode, so you can guys get some overview of what we're gonna talk about. Then we're gonna talk about why static analysis fail or automated static analysis fail in Solidity, and yeah, we will try to explain a new idea or the new research focus, and we'll talk, of course, about what we can do next to improve that research. So the motivation of this research back to 2017, I was like obsessed with big data collection and scanning the entire internet. So I built like IB version 4 stack scanner. I scanned the entire internet for general Web 2 issues, and I was like, can I implement that in on-chain networks? Like, can I do the same? Can I scan the entire EVM networks and find vulnerabilities inside the smart contracts? So I was like, okay, that's a really big challenge because it's even bigger than the IB version 4 stack in terms of data because we have more than 266 EVM compatible network and we have almost 3 billion blocks. If we will talk about bytecodes, that's, I think, too much data to analyze. So the challenge accepted, we started to work on that. So, like, what is EVM virtual machine? You are writing actually just normal Solidity code, and this Solidity code getting compiled into bytecodes or operation codes, and this operation code getting executed by the EVM or the Ethereum virtual machines. That's really basics. So, yeah, as you see right here, this is like the implementation of the operation code within the EVM code. I mean, if you guys took a look at the Ethereum code and the EVM, for some audits, like people who's auditing actual Solidity and people who's auditing the Ethereum itself. Yeah, so actually it's much better to try to understand the bytecodes or if you are trying to reverse engineering the smart contracts, because sometimes if you are trying to analyze malicious contract, for example, you don't have access to the source code, so you will need to reverse engineer the bytecode. So here's like really great technique I'm personally using for reverse engineering the bytecodes. For example, I'm reading the code of the implementation, the Golang, and I'm looking at the instruction, and by practice, you will be able to read that bytecodes just same as the code on the right. So, for example, right here in duplicate or push that address, that's a function selector, by the way. We're going to talk about this in a moment. So you are popping from the stack and picking the next object, and by pick from stack, if anyone here from computer science background, so you don't pop up the value from the stack, you just take the value. And you are just doing conditional jump. I mean, if you read the code, the Go code, and you take a look at the bytecode, it will make sense and it will be just like normal code. So what we're expecting something like that, which is like, okay, what you understand from that. I mean, yeah, you can turn that into disassemble it and turn this operation code into actual values, but still like garbage value. We don't understand that much from it. So how's ETHScan doing it? Like, for example, if you found a malicious contract on ETHScan and they can tell you like, oh, okay, we found some matches for this contract. And when you click, you can find like list of the contracts that match that signature. So that's a breaking down of the Ethereum bytecodes. We got the constructor, we got runtime code, we got the metadata. We got to talk about all of them, but we are all interested in runtime code. So the constructor is actually initializing the contract. Like once you deploy the contract, you're setting the values, the owner of the contract, maybe some other parameters during deploying the contract. It mostly ends with a return instruction with the opcode of F3 hexadecimal. you might have multiple constructors for each, multiple constructor for one contract, because you might import some third-party libraries and so on. So, but mostly they are ending with a return instruction. A runtime code. The runtime code contains actually the stuff we're gonna take a look at. So it contains the function selector. I like to call it the main functionality of the smart contract. It all goes into the runtime code, and the actual contract logic. Like if you are doing arithmetic operation or any transfers, calls, or whatever, they're just going through the runtime code. And inside the runtime code, you will see like the function selector, which I call it like the main function of any smart contract, because an Ethereum transaction is just like one transaction. You are specifying the method ID, and somehow you are calling like call data load, and you are trying to pop the values and try to match the signature of the function. For example, this one right here is trying to match emergency destroy. Okay, if it's equal, it's gonna jump to the offset, okay, which is 37. So once you jump to the offset, you will just land into the actual implementation of emergency destroy. So you can parse that code and you can get some main functions within this contract. But by the way, they are just public functions, because internal functions within the actual coroutine of that function, you will have like some internal jumps. So that function selector contains only publicly exposed function, or the functions that you can interact on the chain with them. So the metadata is kind of useful, because if you are working with some compiler optimization, because the bytecode of, and I will tell you why we're gonna use that later on. Because, for example, I implemented a function. If I compiled it in different compiler version, it might reduce some different bytecodes. So I'm going to talk why we will need that metadata. So metadata contains some information about the contract, like compiler name and compiler version for sure. So static analysis, we are only interested in runtime code, as I mentioned. We want to exclude third libraries like OpenZeppelin and other known libraries, because we really don't need to audit that, because this has been audited before, and we don't really need some visibility about this one. So, and code reuse, like all of Solidity developers, I know how many developers are here. Okay, that's a lot. Like, who doesn't copy paste code for Solidity? Okay, so people are just copy paste Solidity code from different projects. So that's actually generating some sort of signature. So yeah, static analysis, that's right here is the insecure code, and this one just looks fine. I'll tell you why. Like this one, it's just public function calling self-destruct to basic. You can just destroy the contract, send all these to the address you're supplying to this function. But this one here, only the owner of the contract can destroy the contract. This actually looks fine, because this could be a rug pull, but anyway, it just in terms of security. So this one is insecure, this one looks fine. So runs them in static analysis. I'm not gonna mention the name, so you just get, okay, that's insecure, there's something wrong going here. And this one, okay, looks fine, because you're doing like some sort of validation. But if you did like just an internal function and you call automated scanners are lame, and you try just to use the same thing and you pass this contract is really vulnerable, okay? But if you pass it to static code analyzer, it will show you, okay, I don't see anything. I never met that guy. Like, I don't know what self-destruct is. That's because this automated scanners are based on function signature. So if you change the function signature, actually, like you're like invisible for them. And that's why you need code audits, by the way. That's the whole point. You cannot rely on automated scanners. So operation code, OpCode based analysis, how are we gonna do that? How the entire flow is gonna work? So we're gonna get the code, like we have the contract address, we're gonna get the bytecode. After that, we will find the function selector, parsing it. We have like main functions to call, main functions to interact. And after that, like based on that, like we have like the function select signature, which is the X, and jump offset, which is the start of the function. So we are trying from the start of the function or from that specific offset, we are looking for a return value or a stop instruction. Return instruction or stop instruction. And once you find this one, you might have multiple conditional jumbles in that function body, but at the end you will find like a stop instruction or return instruction, and that will be your function body. So what if we could like hash that body? Because hashing, who doesn't know hashing? I think everyone is familiar with what's hashing. So hashing is we are getting like so basic. We are giving inputs and we are having like fixed side output, so we can make integrity checks, and we can detect similarities based on the hashing, the function body. Okay, so we will check if the code is known. If it's already on database in our database, then okay, this function has been copied from somewhere, or this function is open Zeppelin or whatever. If not, we're gonna start our art. So we write a rule to detect this sequence of operation code. Like jump destination, you're just literally landing inside the function, okay, body, and you're duplicating value, pushing, shuffles, and sub, and you're calling self-destruct. So if you found this sequence, okay, without the jump destination, because jump dest is like the entry point of the function body, but if you found that sequence from here till here, you should generate some alerts. Like you should tell, okay, this guy is trying to do self-destruct. But it could be false positive as well, because if you will compare only from that value right here until self-destruct, as we see in the code right here, we have like a caller equal a value and jump equal. If it's not, it will revert. Okay, so what we are seeing here is actually that message. Like we are comparing the message sender, or we are getting it from the caller, and we are comparing it to some object inside the memory, which is like the address of the owner. So if it is not the owner, so it will just revert. So that's a secure version. So what you're looking for at this sequence of instructions just directly after the function body starting. And also you can like somehow we in Halborn we tried to call like multiple collect modifier codes, regular checks, and we had like built some signatures so we can actually detect what's kind of protected and not. And we had like some attack surface analysis, like okay, this function of this contract, anyone can call it. We have like this number of functions exposed to all the chains and stuff like that. So yeah, this is kind of real actual result. This stuff are live on chain, so that's screenshots from the project. So the vulnerability count is, we have the amount of vulnerabilities. Most of them are just maybe like low severity stuff, but also we have high stuff like the self-destruct, but they're kind of most to be test contracts. So there's a developer trying to learn something new, so they're just deploying the contracts to mainnet or testnet or whatever, because that's all combined together. So we have something like we went to scan, and after we scanned all the stuff, we picked like random address and we put the code. We built an scan and we found that code. So that's definitely vulnerable code. So what we can do next, actually we are planning at Halborn to publish vulnerabilities intelligence report, where we'll have like some charts and say, okay, the most common mistakes between Solidity developers is this one. And also we're gonna do some threat hunting where we can find scam tokens and exploits. Because at a certain point, if you're trying to exploit a platform or a protocol, maybe somehow you will need to deploy a malicious contract that's somehow interacting with the other contract, for example, in return-C. So you will need to do that. So we can detect these exploits because we have some known signature, because as I said before, people are doing just copy-paste and stuff like that. So we can also detect phishing contracts, scam tokens, because we are monitoring the chain. We have the entire visibility of the chain. And what else anyone have thoughts about what we can do else? if you can read like the code, if you have signature. Think about an antivirus on your computer. When you're downloading a malware, this malware is getting flagged because it has an no-one signature. But also there is more advanced solution, which is an ADR. Okay, so this ADR is based on user behavior and stuff like that. So we already passed within this tooling or this methodology, we already passed that stage of building an antivirus, and right now we are building an ADR. Okay, so we can analyze that. Okay, that's all for today. If you have any questions, you can ask me right now, or you can just DM me on Twitter or Telegram, both of my usernames. Yeah.